So, my name is Julian Allwood, and I'm here in the University of Cambridge, and very grateful to you for giving me the chance to present to you via this film. So, friendly greetings to you in Kozice. In our research group, we look at reducing carbon emissions, and we're trying to come up with strategies that really make a big difference. Because from here in a university, we're one of the few groups that can really address the questions of scale beyond what's either politically or commercially possible today. And I see this opportunity of making a 200 mile per gallon steel car as a fantastic opportunity for collaborating with you to make a step change in both public and commercial perceptions of what emissions reduction could look like over the next 10 to 20 years. We in our group look at greenhouse gas emissions as our main focus of all of our work, and we're particularly driven by the UK's target to reduce emissions by 80% by 2050. So we use pie charts like these ones to show where the emissions are coming from, roughly 2/3 from energy and industry, 1/3 from agriculture. And within the energy sector, then we have three big areas of focus: the use of energy in buildings, in vehicles, and in industry that makes buildings, vehicles, and the equipment used in industry. This project addresses two of those, and I'm going to start by thinking about the use of energy in the vehicles themselves. This picture is a favourite of mine when I'm giving talks about transport. On the right, you can see a fantastic British innovation from 1959, the Mini invented by Sir Alec Isigonis, famed as the vehicle of Mr. Bean, of course. And it was invented as a highly efficient car for transporting four people at a time that there was a fear that oil was going to become either expensive or short. On the left is what's happened to it since we sold the car to the Germans. So this is the BMW version of the Mini. There's no use of Photoshop in this image. You can see that the car is far bigger. But nevertheless, when we look at the fuel efficiency figures, both cars deliver 43 miles per gallon. So the history of car development, all of that new technology we've invented in cars, has allowed us to make bigger cars with the same performance. We haven't used it to make more efficient cars. You can see on these graphs that data from the US from 1970 to 2010 shows the same story. On the graph on the left, you can see that since 1970, there was a period when we kept the acceleration the same and improved fuel economy during the oil shocks of the 70s. But since then, all innovation has been to increase the acceleration rate of the car with no change in fuel economy. And you can see in the graph on the right that that's because the weight of the car, which reduced during the 1970s oil shocks, has steadily increased. So at the moment, what the customer wants from cars is ever larger cars with ever faster acceleration rates. And yet, what we really know is that the 1959 car with the smaller size and with the lower acceleration rate is the pointer towards what a more efficient car in the future looks like. In the European Union, policy on cars is being driven very much towards electrification of cars, and I'm sure you saw the publicity for the BMW i3 that was launched last year. But when we compute the emissions for that car, assuming the electricity is generated in the UK, then the emissions are nearly the same as the Renault Clio. I chose that as a car of similar performance and size, 10 years older, French rather than German quality of engineering, but nevertheless they're within 10% of each other in their emissions. So electrification is not the answer for producing a low carbon fleet. What matters is size. The graph here shows the cars that are currently on sale in the UK, and you can see that the fuel consumption correlates almost linearly with the weight of the car. So if we want an energy efficient car, then we have to have one that doesn't weigh very much. So the car I think is most exciting as the pointer towards where we want to get to is the Volkswagen L1. The version I've showed here is the 2011 version, which had the passenger sitting directly behind the driver. And this was before they moved to the plug-in electrified version of the car. The car weighs 380 kilograms and it delivers 190 miles per gallon. So it's very nearly at the 200 miles per gallon target, which is the challenge that I think you should be addressing. And of course it's achieved by creating a small, lightweight car. What I think the Volkswagen concept car has shown us is that we now do know what an efficient, low consumption car looks like. It's small and it's lightweight. But what they haven't yet solved is the question of how to make it without greatly increasing the energy in production. So the car is made out of aluminium, magnesium, composites, some ceramics, and they're proud of that because they're calling it an advanced materials strategy. And we don't know the details of what's in it, so we can't do a detailed calculation, but it looks to us as if the embodied energy of making the car is going to be very significantly higher than making the cars that we use today in order to get this gain in efficiency. So ideally what we want to do is to find a different balance between the energy in making and the energy in using. And if we could make a 200 miles per gallon car out of steel, then we'd be able to demonstrate progress on both fronts. Going back to my pie charts for emissions, then you'll see that nearly 2/3 of the emissions arising from industry come from making the bulk materials, particularly steel and cement, as you know. But if we look in the costs of those industries, then nearly 1/3 of the costs of making steel, or indeed any of the other bulk materials, arises from purchasing energy. So for 150 years, you and all the other bulk materials industries have already had perfect motivation to use less energy. And as far as I can understand it, the steel industry is the most energy efficient in the world. Best practice is now within 2 of the absolute chemical limits of separating oxygen atoms from iron atoms. So what that says is that if we want to reduce the emissions of the industrial sector and of the steel industry in particular, we have to use less new steel. We've spent 5 years looking at that, and we've started from maps like this of the flow of steel through the world's economy, and then tried to look at how we could intervene in those flows, what would allow us to use less new steel and still live well. And we looked at 6 different strategies. We had a project with a team of 8 people here, an industrial consortium of 20 partners right across the supply chain. And we found that there were 3 options for using less scrap or for creating less scrap in manufacturing. And they're of course a good thing, but the really powerful strategies are the ones that reduce our total demand, making products with less steel, keeping them for longer so the replacement rates go down, and using the products more intensively. We wrote all of those up in a book which we've called Sustainable Materials with Both Eyes Open, and we've given that away for free, so you can download it if you're interested from this website, or I'd be delighted to send you copies. And naturally that sounds like bad news for the steel industry, but actually it looks to us as if that's the future anyway. Adding more value to less steel is almost the only commercial strategy that we can understand when the market overall seems to be to have global excess capacity. The graph here shows a study of the stock of steel in use in various countries as their GDP grows. What this graph shows is that as countries get richer, the stock of steel in the country rises until we get to around about 10 tonnes per person, at which it stabilises. And that gives us a basis for forecasting how steel use is going to grow worldwide. We know that this pattern has occurred for Western Europe, for Japan, for the US, for Australia. So if we anticipate something similar in China and India, we can forecast the demand for steel in the future. So the second graph here, the top line shows what we think will be the total demand for steel over the next 40 or so years. And you can see it growing from around 1,500 megatons per year today to maybe 2,500 megatons per year. But then if we look at the availability of scrap for recycling, you can see that there's going to be growth in the secondary industry in making steel from scrap, but no further growth required in the primary industry. And I think that's obvious already. Margins are very low at the moment because globally the industry is over capacity, and it looks to us as if it's going to stay there. We don't need any more steel making capacity for the primary route worldwide. So what that says is that material efficiency, adding more value to less new steel, is actually the way forwards anyway for the steel industry. So this project, as well as creating an icon for a future efficient vehicle, also demonstrates the way that the steel industry has to develop in future towards creating more value with less overall production of steel. So I think the opportunity with this project is about raising public perception of steel as the right material for making vehicles in future. That's something which I think is being lost at the moment. If I look up in the Volkswagen website to find out about the L1, what they say is, to make weight savings possible, Volkswagen developed a new system for the manufacture of carbon fibre reinforced polymer. Just 23% of the car is made out of steel. Further savings are made through the extensive use of lightweight materials, including magnesium, ceramics and aluminium. So the PR message that Volkswagen are selling is that the car of the future is not made from steel. But clearly, if we look at the overall life cycle of energy involved in making and using steel, it would be better if we could make these highly efficient 200 mile per gallon cars from steel rather than from the energy-intensive, unrecyclable materials that Volkswagen are using at the moment. So the vision that I'm hoping to share with you and would love to be part of, if this captures your imagination and it looks like a project that you're going to take forwards, is to create the 200 miles per gallon all-steel car. I've put this picture of the E-Type Jag, one of the great glamour pictures of motoring in the UK, something that James Bond was famous for driving in the early movies. Can we make an attractive, commercially exciting car out of steel that delivers 200 miles per gallon, of course by trading size and performance against the overall weight of the vehicle? Can we make it something which customers would want? Can we design it so it could be recycled efficiently, so with separable steel grades, with removable copper, for example, so that we really can demonstrate the closed-loop potential of the materials? And if we can, I think there's an opportunity to make a step change in the public perception of steel and of the future of cars. I think we could get tremendous political attention out of this. If this car existed and could be driven, we could take it round different capital cities to get politicians to come and drive it and use it. I think this would make a fantastic difference to the way that people anticipate how cars might develop in the future. And of course, part of the interest for me would be to be involved with you in celebrating the environmental success story that would be implied in a really good low emissions vehicle, not one that relies on the illusions of electric batteries or in forgetting about the embodied energy of the other lightweight non-ferrous alloys or the composites. So I think a 200 miles per gallon steel car is both physically possible and it's the right time to do it now to change public and political perceptions. So personally, I'm hoping that you get excited about this project as I have done. And I'd love to get involved in it with you if it's something that you decide that you're going to go ahead with. Thanks very much for giving us the time to present. Goodbye.